Hi, I'm Evan, and my goal here is to record the video that I would have wanted to watch when I was learning about the Fourier transform. So let's do that. Basically, the goal of the Fourier transform is to go from a short segment of audio, which is like, say, 1024 individual samples, right? These samples are like, different numbers going up and down representing changes in air pressure. That's the waves that you hear at your ear. So brief audio primer, I guess, first. Then what you want to do is you want to figure out what frequency, like what's the dominant frequency in that audio file. So if you're playing a middle C, then dominant frequency is going to be like 440 hertz. And obviously there's going to be multiple frequencies. What the Fourier transform gives you is just a distribution over a bunch of different frequencies, what frequencies show up the most in this little segment of audio. And you can do that over like an entire audio file, and that gives you a spectrogram, a graph where you plot the Fourier transform up and down the y-axis like this, and then you just plot all these different Fourier transforms along the x-axis. That gives you this graph where the y is frequency and the x is time, and it shows you, if you do it to a piece of music, you can sort of see the melody as if it were a piece of sheet music just from analyzing the audio file. So the way you do this, the frequencies you pick, say you're transforming 1024 audio samples, which is common. The first frequency you're going to be looking at is one where the wavelength is equal to the length of the audio that you're analyzing. So within the segment of audio, you can only expect to see one cycle. That's the first frequency. Next frequency is 2 cycles within your little audio thing, and then 3 cycles, 4 cycles, all the way up to 1024 over 2 cycles. So literally up and down every other sample. That's how many cycles. So that's the set of frequencies you choose. Now for each of those frequencies, first of all, you treat the audio snippet that you're analyzing, you treat it as a vector where the samples are, just the numerical values of the samples are components in the vector. And to take the Fourier transform for each frequency, you like synthesize a sine wave, also as a vector where the components are audio samples. You get this sine wave. And you take the dot product of that with your audio snippet, and you do that for all these different sine waves. And then each of these dot products, you see when you take the dot product, if the phase matches up anyway, then it's going to be positive where this one's positive, negatives where this one's negative, and so it just kind of everywhere it adds to the frequency, and you see that it contains that frequency. If it doesn't have the frequency, then the positive and negatives from the sine wave are going to cancel out, and you'll know that it doesn't contain that frequency. I mean, if you want to know what the Fourier transform is, that's what the Fourier transform is. But there's details, right? There's stuff you have to take care of. So most important thing that you need to take care of is, what if the phase of a particular frequency in the audio snippet that you're analyzing doesn't match the phase that you chose for the sine wave to take the dot product with? And there's a clever thing to get around that. Obviously, if it's 180 degrees out of phase, positive and negatives are exactly opposite, then you're going to get a large magnitude still, but it's going to be negative. So that's fine. If you want to know the magnitude of that frequency, you can just take the absolute value. The clever thing that you do is that for the 90 degrees out of phase case, you actually, in your sine wave vector that you're using to take the dot product, you add a complex component so that each component of the vector is a complex number with a real and imaginary component. And so the result of the dot product is going to have a real and imaginary component, and the real component corresponds to the one with 0 phase, and then the imaginary component corresponds to the one with 90-degree phase. And if you actually take the magnitude of that resulting complex number, then you get the correct magnitude for that frequency regardless of what kind of phase was in the audio snippet that you're analyzing. So since this Fourier transform, each component of the result is just a dot product. Really, you're just taking a bunch of dot products. That is literally matrix multiplication. So you can express the Fourier transform as multiplication by the specific matrix. And that is why, for example, that's why the Fourier transform is considered to be a linear operator. Obviously, it doesn't deal with lines, it deals with sine waves. But because you can express it as multiplication by a matrix, it has the properties of a linear operator. It just doesn't look like a linear operator because we do all this weird stuff. It has complex components and stuff. You can't really interpret it as a linear transformation easily, but it is one. And this is where the Fourier transform gets really useful, not just for audio processing, but it can be adapted for other stuff. Anyway, the point is that this matrix has special self-similar structure. It means that multiplication by this matrix can be done with a lower time complexity than matrix multiplication in general. The naive implementation of the Fourier transform would be order n squared, where n is the length of your audio sample thing. But the fast Fourier transform, the implementation that takes advantage of the matrix self-similarity, the time complexity is n log n, which is really good. So Fourier transform equals really fast. The other issue with Fourier transform that you have to take care of is that if you just you're analyzing a song file, you select this little portion with the 1024 samples and you apply Fourier transform, it's going to add a bunch of frequencies that aren't there. And the non-technical explanation for why it does that is, if you were to just select that little region and play it, you would hear a click when it starts, and you would probably also hear a click when it stops. And that's because the signal that you were hearing immediately jumped from 0 to some random value that segment happened to start with. And it's a little weird, but the Fourier transform basically hears that click too, and it's going to interpret that click as a bunch of stuff in frequencies that aren't really there. So if you're trying to make a spectrogram of an audio file, you're taking all these Fourier transforms. For each little segment of audio, you need to essentially fade it in and then fade it out so there's no clicks. And you typically do that by multiplying it by a windowing function, which is just like a little normal distribution looking thing. And there's ones that work specifically well for Fourier transforms. You multiply it by that first, and then you take the dot product with all the different frequencies and stuff, and that's your Fourier transform. So that's that. That's Fourier transform, and that's also how you do spectrograms. And the technical name for spectrograms that people sometimes use is short-time Fourier transforms. That's right. The short-time Fourier transform, STFT of a signal, is its spectrogram. Right. So before I said that spectrograms look like musical notation. They sort of look like musical notation. The problem is that the note frequencies are really squished together at the bottom compared to musical notation, and really far apart at the top compared to musical notation. It's because musical staves are actually a logarithmic scale, and in terms of frequency, and spectrograms are a linear scale in terms of frequency. So often programs that display spectrograms will have an option for stretching out the FFT so it forms a logarithmic scale. But this is where the constant Q transform comes in. Because the idea behind the constant Q transform is that for analyzing music, it would be really nice not just to display the Fourier transform on a logarithmic scale, but to actually have accuracy that corresponds to a logarithmic scale. So more accuracy than a Fourier transform at the lower frequencies, and less accuracy than a Fourier transform at the higher frequencies, so it's more even. And the constant Q transform is exactly that. Instead of taking the dot product with linearly spaced frequencies, you do dot product with logarithmically spaced frequencies. You get to choose the spacing of the frequencies. So that's what a constant Q transform is, but there's a couple other details. In a constant Q transform, when you take the dot product with these higher and higher frequencies, you actually take shorter and shorter segments of audio to do dot product with. The reason for that is that the frequency that you're taking the dot product with is considered a filter. You're filtering the audio by that frequency. So in the constant Q transform, the higher frequencies, the filters you use have larger bandwidth, meaning they'll accept more variance in the frequency that's being fed in. So that's how the frequency bands at the top that have more spacing between them also kind of fill in that spacing by accepting more frequencies. So that's if you're seeing a constant Q transform, you're like, why do they even bother decreasing the lengths? That's why they're decreasing the lengths at the top. So that means you're also choosing a shorter window function basically for the higher frequencies. So now that you understand that, the issue with the constant Q transform now is that the fact that you're analyzing smaller pieces of audio at higher frequencies means that if you were taking a spectrogram and you spaced these constant Q transforms so that the high frequencies, covered the entire piece of audio, then you're going to be doing a bunch of redundant calculations at the low frequencies because they overlap so much. So for constant Q transforms, there's actually a paper about this. I don't know what it's called. I'm going to cite it in the description. I guess that's how you cite things in YouTube videos. Or maybe I'll put it on the screen, whatever. The point is, this paper has this, formalizes this solution for getting around that. What they do is they no longer take a constant Q transform at a specific time slice. What they do is they say, oh, we're just going to take the lowest frequency and we're going to choose a spacing for it, and then we're just going to have different spacing for each frequency. Like, obviously that might be a bit problematic if you want to look at a particular time slice and say, what are the frequencies here? And it might make displaying it a little more complicated. But, I mean, that's a trade-off you have to make. So that's what this kind of definitive paper on constant Q transforms addresses. It so happens that even though with constant Q transforms, you lose that matrix self-similarity that allows you to do it fast. What you can do fast is you can kind of use the Fourier transform a different way. I don't know all the details. If you want to learn more about it, try first looking up FFT convolution. And what you can do with it for a single frequency, you can do that dot product at regular intervals in time across the whole audio thing. And that's also going to be n log n time complexity in relationship to the length of the audio. So you just do that for every frequency, and the time complexity, the time complexity for Fourier transforms is n log n times the number of time slices you choose, and in this case it's n log n times the number of frequencies you choose. So overall the time complexity for creating a spectrogram stays basically the same. So yeah, hopefully that helps you to understand the Fourier transform and demystifies the constant Q transform a bit, because my idea with this video is there's lots of tutorials on the Fourier transform. Probably there's some that explain it better than me, but what I've got that they don't is I'm going to explain the constant Q transform. And because I think that most explanations of the constant Q transform are like really technical and go into the math a lot, and I don't like doing that. So well, that's my explanation. See you later. Bye.